this comes under the category of a general result, because I'm not going to consider any system here. So, we have a system, and then I'm going to call this. We have a, let's say, Hamiltonian of the system H of Q bar and P bar.
Sir,
Yeah.
sir, I have doubt regarding the previous class.
Yeah. What is it now?
Sir, can you please explain how Lord Raleigh came up with the Rayleigh-Jeans law, like how he considered the stationary modes and came up with the new square term?
Okay. So maybe I will do it after completing this lecture, and
Okay,
that is
sir.
also an application of equipartition theorem. So we will take that up after.
Okay, sir. Thank you.
So this is the Hamiltonian. So let me simply denote some omega to represent this Q bar and P bar. I'm simply going to call this as omega. So omega is basically a shorthand notation to tell you Q1 up to Q3n and P1 up to P3n. And this is just the notation. And I want to ask a question that so we would like to uh, we would like to we would like to calculate the ensemble average of some xi into partial derivative of h with respect to some xj over canonical ensemble at some temperature here, of course, where this xi comma xj are any two, any pair of omega. So you can choose them to be both positions, both momentum, even arbitrary pair. So we will denote it in this following fashion. So let's say I have xi into dou h by dou xj. This is the notation, I mean, the kind of thing that we say for an ensemble average. But how this is written is something like this, because you can write this as integral over d omega into xi dou h by dou xj into e to the power minus beta h. Okay. So this is the quantity whose average we are interested in, and the canonical probability distribution is given by this. Okay, so remember, canonical probability is given by probability equal to e to the minus beta h divided by integral over d omega into e to the minus beta. Okay, so that is this divided by integral d omega e to the minus theta. Okay. So now we will try to perform this integration. But before we do this integration, we will try to just consider the numerator. So consider,
Sir,
yeah.
sir, can you tell me that what does that xi del h by del xj represent?
Uh, okay, so this is something which we will understand later. But right now, this treat this as some kind of a see. I can ask and some leverage of any function. So this is one function which I am defining, and what this function is useful for, we will understand when we get the result finally. Okay, so just hold on till we complete this. So consider the numerator, and I'm going to write this numerator in the following fashion. Uh, so let us say that you can write this as integral 1 divided by integral 2. Okay, so integral 1 is equal to, I will write it in the following fashion, d omega into xi. So I can write this as dou by dou xj into e to the minus theta h. Okay, so if I write like this, what happens? I get minus beta into e to the minus, that is e to the minus beta h into minus beta into dou h by dou xj. Correct? So note that dou by dou xj of e to the minus beta h is equal to e to the minus beta h into minus beta into dou h by dou x. So I have this extra minus beta, so I will divide that by this outside. So this will be my numerator. So now I am going to rewrite this one in the following fashion. That is minus 1 by beta into integral over d omega a integral dxj. I am actually, see, this d omega is a product of all qi's and pi's. Okay, but I'm going to I'm going to show that I'm just taking one particular dxj out, and this is remaining. All other things are there in this dxj. Okay, that is let me take this and then write this as a and dou by dou x into e to the minus theta. Okay, so here d omega is equal to product over j or some k, you call it dxk, all of it. Whereas d omega of j is equal to product over k dxk, but k is not equal to k. That means other than dxj, all other things are there in this one. That is the meaning of this. Now what we can do is, so consider integral over xj and uh, do an integration by parts. Do integration by parts for integral over xj. That part of the integral. So I will consider u to be xj and dV to be dou by dou xj of e to the minus beta h into dxj. So this is your dV. So this will tell you that your du can be, sorry, this is xi. Have to be careful. Du is equal to dou xi by dou xj into dxj, and v is equal to e to the minus beta h. So our integral can be written. So the integral I1 can be written as minus 1 over beta. I have now integral over d omega of j, and then there are two terms for the thing. The first term is xi into e to the minus beta h, xi into the beta h at so there is some lower limit for this xj and there is some upper limit for this xj. So this is whatever are those boundary values minus integral dxj into dou xi by dou xj into e to the minus beta. Okay. Now let me argue that so note that the Hamiltonian is equal to sum over I some pi square by 2m, the kinetic energy, plus some potential which will depend on r, which can be written as v of ri, or it can in general be left. So let me leave it like this. It will depend on, of course, ri. Now the point is whether xi. So suppose xj is one of the momentum coordinates. So one of the momentum coordinates. So if it is one of the momentum coordinates, then what happens is in whether this is going to minus infinity or plus infinity, because we have this pi square here, so this is going to be plus infinity. Okay, so uh, h actually goes to infinity as xj goes to xj lower limit, or xj goes to xj upper limit. Okay, so this is what happens if this is one of the momentum coordinates, and because of that, e to the minus beta h, goes to 0 at both the ends. So this term will go to 0. Now, what happens if xj is not a momentum coordinate? This is because of this kinetic energy term. Okay. So suppose if xj is not momentum coordinate, but it is one of the coordinates. Okay. So if xj is one of bar, then what happens as xj goes to xj lower limit, Okay, so let's say lower limit, which is which may be minus infinity. Okay, or xj goes to xj upper limit, which may be plus infinity. Okay, but whatever is this, then your your v actually goes to infinity. That means you have a potential such that it will not allow the system to go to those extreme points. That means there is a localization. That means that happens only if the potential goes to infinity. So because h is t plus v, since h is equal to t plus v, if it is a momentum coordinate, it is because of t that h goes to infinity, and if it is one of the coordinates, it is because of v that h goes to infinity. So h also goes to infinity, and therefore e to the minus beta h goes to 0. So this set of arguments will tell me that this boundary term can be made 0, so we don't have to worry about that term, and so that leaves this I1 is equal to, there is a minus sign here and there is a minus sign here, and these two minus signs will become plus. So I have 1 by beta and integral e omega of k into this particular term. You know from basic calculus that it is a delta ij into dxj into e to the minus beta h. So you can write this as, this beta can now be written as 1 by beta can be written as kbt into delta ij into integral. Now I can combine this and then write this as simply d omega into e to the minus beta. Now you recall that this is essentially, so this is equal to kb t into delta ij into it, that is the denominator. So the average value of xi into dou h by dou xj, xi into dou h by dou xj is equal to, you know, it is I1 by I2, which is equal to kBT into delta I. So our result is that our result is simple. What we have is, if we have xi into dou h by dou xj, dou h by dou xj, the ensemble average of this quantity is kBT to delta I. Okay. That means whenever xi and xj are same, then you have the ensemble average is kBT. Otherwise, the ensemble average is 0. So this is a very general result, and we'll see what is the meaning of this result. Now let's say that so let us say in first case, I'll this as case 1. Let us say that let xi be some pl, is a momentum coordinate. Okay, then from Hamilton's equations, from Hamilton's equations, you can say that dou h by dou pi, what will that be equal to? It is equal to qi dot, correct? That is, this is qi dot equal to h by dou pi. So this implies that there is something called Pi into Qi dot, Pi into Qi dot is equal to K. Okay, Pi into Qi dot is equal to K. Now you can say that this is for a particular I, but then you can ask the question, what happens if I take all I? So there is something called sum over I is equal to 1 to 3n. There are 3n. So I have taken one of them, but there are 3n momentum coordinates, right? So if I sum over all of them, and then I ask what is Pi Qi dot, Pi Qi dot, I have something called 3n. Okay. So this statement is called equipartition theorem. Okay. So because you can see that for example, let's say that you have uh, so let's say that consider a general quadratic Hamiltonian. Okay, that means your QIs and PIs enter quadratically. That means it is not necessary that it QI square and PI square, but it can be QI into PI also. But there are only quadratic terms. Now, if you have a quadratic Hamiltonian, then through an appropriate canonical transformation, we can write the Hamiltonian as so let us say H can be written as sum over J is equal to 1 to, okay, so how many ever degrees of freedom are there? Let's say 1 to F, then AJ into PJ square plus some BJ into QJ. You can always write this capital P and capital Q are canonically transformed position and moment. So you can always, every quadratic Hamiltonian can be brought to this form through an appropriate canonical transformation. Okay, so now we can ask this question. So you say that suppose if you ask what is rho h by rho pj, rho h by rho pj is actually 2 times aj and pj. Okay, 2 times aj and pj. That is what you get from here. And rho h by is equal to 2 times pj and qj. Okay. So now if you ask this question, that is you have.
Sir,
Yeah.
Sir, the summation sign, what are the summation signs?
Summation?
Uh,
No, I don't have summation sign when I'm taking a derivative with respect to one of the components. Right?
okay, sir.
So what I'm trying to say is I put same j, so that's probably the reason for confusion. So if I want to write dou h by dou pk, so that is nothing but sum over j is equal to 1 to f aj into 2 times pj into rho pj by dou pk. And this gives you, sorry, dou pk, and this gives you a delta jk. That means this j summation will simply give you ak into 2p. Correct? So that's how I am writing it like this. I'm writing it directly, but summation will not be there. So now if you ask this question that okay, so now let me write pj into dou h by dou pj. So if I write like this, that will be 2aj into pj square. 2aj into pj square. Okay, so if I look at the average value of this one, okay, so that is equal to average value of this, that is given by uh, 2 times pb. Correct? Because aj, sorry, so that is equal to kb. Correct? Because pj, dou by dou pj is, we have seen that this is simply kb. Okay, so now what happens is, now what happens if I take here also, I will have a similar thing. Then you can see that um, this can be written as, uh, so if I take sum over all these quantities, okay. Uh, so when I take what is the average value of h, average value of h, basically sum over j is equal to 1 to f aj aj pj square plus bj 2j square. Okay, so when I do that, then I will have so aj pj square average will be half kt, and this will be another half kt. So you can see that there will be f times kb. So uh,
So,
yeah.
like, is it possible to take that expectation term by term? Like if take an expectation of whole each, so you have divided that expectation into the term of aj pj square plus bj pj square. Can we take
Okay.
that always? Or
Okay. So that's a good question, but in this particular case, it can be taken. But let me also come back and tell you when can it not be taken. Okay. So now what I am trying to see here is that at this, or in other words, let me even probably write it here. That if I can write this, let me take this and then write my aj as 1 to rho h by rho p. Okay. So I can write it like this, and similarly you can write down bj as 1 by 2 qj, 1 by 2 qj into rho h by rho qj. Okay, and then you substitute this aj and pj in the Hamiltonian. So we have Hamiltonian is equal to sum over k is equal to 1 to f 1 by 2. 1 by 2 is common, so let me take it outside. So this pj in the denominator will actually cancel with one pj here. Okay, so you can see this. Then you can write this as pj into dou h by dou pj plus qj into dou h by dou qj. Okay. Now there are f such quantities. So you can see that this is nothing but half into, there is a kBt coming from here and another kBt coming from here. So there is half into 2 times f of kBt, and that is what gives rise to kBt. Okay. So the statement that we have here is the following. So for every degree of freedom, for every degree of freedom, that enters Hamiltonian quadratically uh, there is a share of half kBt of thermal energy. So if you are actually trying to calculate what is the total internal energy of a system, so this theorem will definitely be useful. Like for example, you can find out how many number of degrees of freedom are there, and then assign half kT of thermal energy for each degree of freedom. Okay, so for example, let's say that I have so let's say that I have n number of particles. Okay, so let's say I have n particles confined to move freely on the surface of a sphere. Okay, maybe there is no such system, but let's argue that we have some such system. Okay, confined to move freely on the surface of a sphere. Now you know that this is a free particle, and hence there is no potential, but there are 2 degrees of freedom, namely theta and phi. These are 2 generalized coordinates, and corresponding to these 2 generalized coordinates, there is a generalized momenta p theta and p phi, and they both quadratically enter into Hamiltonian. So it's a free particle, so they both quadratically enter, and since they both quadratically enter, we have half kBt for this and half kBt for this. So the total energy per particle is kBt, and hence you have n particles. We have total internal energy will be simply n times kB, and from there you can say that the specific heat is simply n times kB. So this actually simplifies to some extent that this equipartition theorem is at least valid for all systems at high temperature limit, and hence estimating energies and specific heats are very easy if you have this equipartition theorem.
Sir,
Okay, yeah.
so for this n particle case, how can we define the potential energy?
So right now I am saying they are moving freely, so there is no potential energy. So the potential energy is 0. So I only have a kinetic energy.
Okay, sir. But there is a constraint.
Yeah, this is a constraint. So one can that is why I am using these generalized coordinates. These generalized coordinates do not violate constraint, right? So I will have some quadratic term involving p theta and p phi.
And so one small doubt,
Yeah.
FKBT in the case of FKBT, because F is number of degrees of freedom, so shouldn't that be F by 2?
Um, where here?
So FKBT.
Ah. So the point here is that the number of degrees of freedom, if in this particular case, we have 2 degrees of freedom, but since there is no potential, I have half kpt for this and this. Suppose if there is a potential which is also quadratic in theta and phi, then I will have double the contribution, right?
No, sir, I'm saying that FKBT, the Hamiltonian equals FKBT.
That's correct. That's what I have written here, right?
So shouldn't that be F by 2? Because
So
F is
that's
a
what. So now it all depends on if you are saying degrees of freedom, we are only talking about these Qs. Okay, we are only talking about Qs. Then there are associated P's also, right? So if these also enter quadratically, these also enter quadratically, then it will be. Or if you are saying, okay, I am going to call f as both number of P's and Q's, then it will be f by 2.
okay, sir. Yes.
That is the only difference in terms of how we define it.
Okay, sir. Thank you.
Sir,
And yeah,
sir, can this term enter as cross terms like p theta p5 or multiplication of q and p like that?
yeah, you can have that is in your Hamiltonian, you can have cross terms. Okay, but what I'm saying is that you don't have to worry about those cross terms because you can always think of an appropriate canonical transformation and bring the Hamiltonian to this form if it is quadratic. So important, what is important is that the Hamiltonian is quadratic. If it is quadratic, then you can always bring it to this kind of a form.
Okay, sir.
Okay. So I also wanted to make another remark here is that what happens if it is not quadratic? For example, let's say that we have a system. So consider a particle moving in a one-dimensional potential. So one-dimensional potential given by, let's say, v of x is equal to some constant v naught into some x to the power n. Okay, let's say we have some potential. This is not quadratic potential because your Hamiltonian is equal to p square by 2m, just one degree, one dimensional problem, p square by 2m plus v naught into x to the power n. So here p enters quadratically, but x does not enter quadratically. So now if you take if you take x and then dou h by dou x, okay, and then take the average of this quantity, and according to our result, that should be equal to kb. Correct? So now what happens? Your dou h by dou x, is equal to n into v naught into x to the power n minus 1. Okay. Whereas if you ask what is x into dou h by dou x is equal to n v naught into x to the power n. So if you ask what is the average value of this, x dou h by dou x average is nothing but n into average of your potential energy. V naught into x power n is your potential energy, and that is equal to kBT. Okay, so then the average potential energy is given by kBT divided by n. Okay, so this is result. Average kinetic energy is average kinetic energy, average value of p square by 2m is kBT by 2. Okay, whereas average potential energy is kBT by n. So what will be the average energy here? So average energy is kBT by 2 plus kBT by n. So this is not same amount of energy for potential for x and p, whereas the average potential energy is n, and this n depends on this power. Of course, if it is 3, it is 3; it is 4, it is 4. If it is 2, of course, it is same. Quadratically, it enters into the Hamiltonian, so it will be kBT by 2 for that. So this is another remark which we should keep in mind, that the equipartition theorem has an important thing, that it has to enter quadratic. Now, suppose if okay, so I think that is one part. Then let us look at case 2. We have so far talked about case 1, and let's look at case 2. And case 2 is let us say that this xi, whatever we have talked about, is one of these qi's. Okay. Let's say this xi is equal to qi. Earlier in our case 1, we said xi is pi. Now let's say this xi is equal to qi. So from the Hamilton's equations, what is dou h by dou qi? Dou h by dou qi is minus pi dot. Okay, so we have xi into, or in other words, qi into dou h by dou qi, into dou h by dou qi. This is equal to minus qi into pi dot, minus qi into pi dot. So the average value of qi into pi dot, qi into pi dot is equal to minus kb. This minus sign is because of this minus. Okay. Now, if you look at this, this is like a position, and this is like a force. Okay. So if you there was a definition which was given by Clausius, defined something called Virial. So what is a Virial? So let us call this as V. V is equal to sum over I is equal to 1 to 3n, average value of qi into pi dot. Okay, so this is equal to minus 3n into kb. In classical mechanics, I am sure you have probably come across this Virial theorem. So that is related to average kinetic energy and average potential energy, especially in central force problems. You might have seen this. So this is, so now this statement, just like we had equipartition theorem, this statement is called Virial theorem. Okay. Now, supposing if you have, so consider, let's say, consider an ideal gas. So let's take an ideal gas in some volume. Bounded by a surface. Okay. So if you are trying to calculate this virial for that, which is given by sum over Qi and all the forces acting on those particles, average value of Qi and Fi. This can be written as uh, you can write this as force is what? What force is actually the pressure. The pressure uh, acting on the molecules by the boundary. So you can write this as minus a pressure, and pressure into the area will give you the force, integral of R dot T. Ts is the surface area, and you integrate over the entire closed surface of the boundary. This is how you define this video. Now the negative sign here, negative sign here is because uh, ds is outwardly directed, whereas force is directed inwards. So that is why we use a minus sign there. And now you can see that this can be written as, I can use divergence theorem and then write this as integral over volume divergence of R into d. Now note that divergence of R, del dot R, is simply 3. So this is equal to minus 3p integral dv over the entire volume. Will simply give you the volume. So that's equal to minus 3p. So from Virial theorem, we know that minus 3pv is equal to minus 3n ab. Okay, this is using Virial theorem. So that means you can now cancel 3, cancel minus sign, and you get PV is equal to NK. This is the equation of state of ideal gas, which we are able to derive from the Virial theorem. Now, this is not the only use of this result, because you can use this. Okay, so so let me also make this remark that this, so the real application of this is so we can use this to obtain approximate equation of state. Approximate equation of state for interacting systems. Okay, so please keep this in mind, and we will try to work out at least one example where we can use Virial theorem to get equation of state for an interacting system. So these are the two theorems, and this is the advantage of writing, knowing these two theorems, equipartition theorem and So, so one of the, so at least I will tell you two instances where this equipartition. So, equipartition theorem was first uh, discovered by Boltzmann. So, equipartition theorem was due to Boltzmann. And Boltzmann used it, as we discussed earlier, to understand Dulong-Petit's law, and he also uh, this was used quite a bit till Einstein's theory of specific heats have come into picture, and so Rayleigh-Jean's law was also one of the applications of this equipartition. So in Rayleigh-Jean's law, what so now Devanjan, you can ask what is your exact question on Rayleigh-Jean's law.
So the question is, there is a nu square term,
Correct.
8 pi nu square by c cube kbt.
Correct.
So where does the nu square term come from? The kbt term comes from the equipartition theorem. Nu square term comes from, I read that it comes from the stationary modes.
Correct.
So I didn't understand that.
Okay. So okay. So now, if you look at this Rayleigh-Jean's theory, or whatever you call Rayleigh-Jean's law, so you know that there is a black body radiation which is universal. That means the radiation spectrum does not depend on the size of the black body or shape of the black body, what is the cavity dimensions, etc. So they have used, suppose let's say that you have a cubic box. Okay, suppose if you have a cubic box, then you can say that, okay, I have some kind of a cubic box, upside L, okay, on all sides I have L, and then there is so there is a radiation. So they assume that if your radiation is in equilibrium, between radiation and walls of the walls, that implies that the electromagnetic waves, EM waves, are in standing wave pattern. And standing wave pattern. That is what was the assumption. So if they are in standing wave pattern, so you can see that you can get this condition for the standing wave is that if you have L, then you can say that it should be n times lambda by 2. Is it correct? N times lambda by 2. Or you can write down this lambda to be E over mu, and then you can write this as n C over mu R2. Okay. Or you can say that this n can be written as twice L by C into mu. So this n is an integer. Okay. So if you have this situation, then you want to develop this theory for all. So there can be in one direction there can be n, in another direction there can be m, like that. So, but this is a typical relation. So you can say that suppose if you have let's say you have n1, n2, and n3. Okay. So now if you say that you have you want to calculate how many number of modes are there with some value of n. So let's say this is your n, and then there is another value of n plus dn. So the number of modes between n and n plus dn is given by 4 pi n square into dn. Okay, this is proportional to that. Into, of course, the number per unit, some kind of a number per unit volume in this n space. So in this n space. Now you can see that this is 4 pi into this n is taken from here, that is 4l square divided by c square into mu square into dn will be another 2l by c into d mu. This is change in n is given by this. So you can see because of this you have so you have something like is equal to 4 pi into 8. This L square into L will be L cube, that is the volume, mu square divided by C cube into d mu. And of course, you know that this particular values of n are only positive integers, and hence they are positive integers. Only 1 octant of that one will be contributing to the volume. So I'll have to divide by 1 by 8. So that is equal to 4 pi v mu square, like that. But then you also take into account the two polarization modes, the two polarization states, two polarization states for each timing wave. That will have a multiplication of 2, and so there is another 2 sitting here. So this 2 and 2 will cancel away, and finally the number of modes, which you can call it as some g mu d mu, can be written as 8 pi. Um, uh, so this you can, if you can define this as number of modes per unit volume. So that is what is interesting in energy density. So that is simply 8 pi mu square by c. So this is basically the argument which Rayleigh has used in deriving this. But this is very different from what Max Planck has. Max Planck also derived this relation, but his argument was completely different, and it is much more a clear and proper application of classical electrodynamics. This is some kind of a counting, and this is what was the argument which Rayleigh had when he had developed this. I do not know, maybe Rayleigh did not know the work of Planck. That is possible because those days communication was not that great. So it may be that he does not know and he tried to get it on his own. But we will see in our course later that both Rayleigh and Max Planck, they derived this relation from classical electrodynamics, and everybody else who did this black body radiation subsequently, including Einstein, Debye, Lorentz, and Arnfest, anybody who did black body radiation, they have used this 8 pi nu square by c cubed. Either they have taken it from like what Rayleigh has done, or they have used Planck's result. But they have not derived this from. So it is always from classical electrodynamics. And if you look at the system of, the history of events, S.N. Bose, one of the objection of S.N. Bose was that when you say you are doing quantum theory, why should you derive this relation from the classical electrodynamics? You should also derive this from non-classical means. So the actual non-classical electrodynamics derivation was given by S.N. Bose, where he did not assume any classical electrodynamics for this. Okay, so that is what we will study when we go to quantum statistical mechanics. That the proper, okay, is also proper, but the correct non-classical derivation of this 8 pi nu square by c cube comes from S.N. Bose.
Okay, sir. Thank you.
Okay, so I think the other question is what Abhijit asked. So suppose if you take x1 is one random variable and x2 is another random variable, then you can independently talk about average value of x1 and average value of x2. But when you take x1 plus x2 as a random variable, now if I take the average of this x1 plus x2, now the question is, can we write this as average of x1 plus average of x2? That is this averaging process a linear process? Like this, will it divide among themselves? Now, the idea is that there is a concept called there is a concept in stochastics called there's something called IIDR. That means independent and identically distributed random variables. Okay. So if you are considering independently and identically distributed random variables, that means there is no dependence. So the values that x1 is taking is completely independent of what value x2 takes. In such cases, we can write like this. But we may have situation where there is some dependence, some conditionality. In such cases, we cannot write like this. And in our case, all these QIs and PIs, we consider them to be independent, and hence it is fine to write them like that. Any other question?
Sir, can you go back to the initial derivation where I didn't understood a step? The delta is a right, the delta.
Today's derivation.
Yes. So here,
Okay. Which part?
from this I1 equal to minus 1 by beta, from this line to the next line I1 equal to 1 by beta d omega j. There you have taken xi in the first line xi e to the power minus beta h xj lower limit to xj upper limit minus from that line to the next line.
Okay. So yeah. So you understand that this partial derivative of xi with respect to xj is delta ij. That you
Yes,
understand,
sir.
right?
Yes, sir.
Okay. So I think so that means you are not your doubt is with respect to these arguments that have made this term 0. Correct?
First term is 0 then. Last term is
No.
non-zero.
So this last term is what I have written here, right?
Okay,
So
sir.
what I have written here is this last term.
Okay, sir.
So this first term is 0 because of these arguments.
Okay. And so from there, from that
Uh,
second line to the next line, there we had d omega j. So then we have
uh,
taken only d omega.
so d omega j is without dxj, no? So
Yes,
this into dxj will simply become d omega, that's all. So this into this is simply d omega. Then this exactly becomes the I2 that we have left behind, that is denominator. Okay, I have called this denominator as I2, right?
yes, sir, I understood that.
Uh,
Sir, in the sir, hello.
Yeah, go ahead.
So in the Virial theorem part, the surface integral, that part I didn't understand properly. Like I can understand from a dimension analysis point of view that why the dimension matches with the Virial, but why surface integral is taken, why r dot ds I don't understand.
Okay. So basically, what is the force acting on the particle? So imagine that you have got some kind of a volume like this, and then these gas particles are there. Okay. So now let's say that when the gas particle comes here, okay. So now let's imagine that we have some coordinate system, and let's say this is your R, that is the gas particle, and then this gas particle will immediately bounce back because it cannot go. That means I can imagine that there is a force, which is basically whatever is the pressure that the particle is sent back. Okay, so that means I can see that there is a at this point there is a force acting in this direction. Correct. So now that force. So if I consider there is a small area ds here, now this ds is in this direction. Okay. Now p times ds, p times ds with a negative sign is the direction of the force in the opposite direction. Correct? Do you agree?
Yes, sir. I agree.
Okay. So then this I have to multiply that with qi. Okay, and I have to do this element by element. Correct. So that means I am going to now write. Uh, so the virial definition will be, this is my force. Okay, so this is my force. Okay, so now my virial definition is R dot F. Okay, that means minus P into R dot S, and now this can happen anywhere on the surface, so I integrate over the entire closed surface. Okay, so that is how the virial can be defined.
Okay, sir. Thank you.
Okay, so I think I do not want to start another now because another calculation to complete. Let me make some comment on states into the mind. This is uh, so you can see that beta is 1 by kbt, and hence beta into e I is dimensionless. Dimensionless, and hence this jet. So we should have the partition function to be a dimensionless quantity. Now, when you take a classical system, we have written z as integral over dq bar dt bar, integral over dt bar dt bar e to the power minus beta h of q bar p bar. Okay, so up to this, the dimension is q into p raised to the power whatever 3n. But to make this dimensionless, we divide this by 1 by h power 3n, so that this becomes dimensionless. Okay. So we had So in general, uh, in general, if you have a partition function which is given by sum over, you can even say distinct energies, epsilon e to the minus beta epsilon, and if if E is continuous, then if you want to write down this Z as integral over d epsilon into e to the minus beta epsilon. Now what happens if you do that? This integral will have dimension of energy. This integral will have dimension of energy. But Z has to be dimensionless. And hence I must divide something, or I must have some constant which will have the inverse dimension of energy. Now, one thing that usually is done is when you are converting this, it is not just this, but there is something that is multiplied here. Okay, so this is something that is multiplied is called density of states. That is, suppose let's say that you have these energy states like this. Okay, so we have some energy states like this, and we are going to continue continuous integration because these energy levels are so dense. So suppose you take energy E and then look at some small variation d epsilon, and how many energy levels are there in this energy difference. This is proportional to, probably sometimes proportional to energy. So we can say some A of epsilon into d epsilon as number of whereas this is also dimensionless. So A of epsilon has dimensions of 1 by ns. So what one does is that you write this here at A of epsilon, so that this entire thing, that this and this as such becomes dimensional. Okay, so the two occasions which was pointed out by Ashutosh was, first one was the question of black body radiation, where we had written down Z is equal to integral d epsilon into e to the minus beta epsilon. This is a classical theory of radiation and black body radiation. Okay, and we have of course obtained the correct result, but then this problem that he pointed out existed here. And the second example is with respect to writing the Z1, which is given by integral d omega, a solid angle, and then e to the power beta mu e cos theta. Okay, so this is another example where you have a classical, this is called Langevin theory. Okay. So in principle, you have to define some density of states here, and you have to define some density of microstates or whatever A of omega here. Okay, but now it so happens that in these cases there is some uniformity, in the sense this A of epsilon does not depend on energy. A of epsilon does not depend on energy, and hence we have something like in these particular cases. So this is some constant. So in these cases, A of epsilon in case 1 is constant, and A of omega in case 2 is also constant, which means you can actually multiply with that constant, and that constant has the dimension of 1 by energy, which will make this Z or Z1 in these respective cases to be non-dimensional. So he was asking a question whether this constant is 1. If the constant is 1, then exactly what we have done is it will go through. But if it is constant, that is enough. It need not be 1. Even if it is constant, that constant will not bother us in getting thermodynamic properties. So I don't know if Ashutosh is listening, but this is what I think is.
Yes, sir. Sir,
Yeah.
yes, sir. I am listening. I fully understand that.
Okay. Okay. So if there are no questions, then maybe we
Sir, sir, excuse me, sir.
yeah.
Sir, sir, you said that in these two cases, it happens that these density of states are some constant quantity.
Uh,
So these things are to determined experimentally, or we can give some physical reasoning to.
so you're asking, can we show that it is uniform? I mean that the density of
Yeah.
state is constant.
Yes. Yes, sir. Yeah.
I think we should be able to show. You can try. You can try, and I will also try.
Okay, sir. Sir, in case of classical ideal gases, we just took it to be 1 over h power 3n. I mean, we did not derive that.
Yeah. So
We just took it.
that is also, that means basically the constant there is 1 by h power 3. So that is why I am saying it is constant, because it is actually the case in all the classical situations. It will be some other constant here.
Is it because of the system itself is non-interacting within itself, as like classical ideal gases that we are taking, there is no interaction between particles?
No, but even if particles are interacting, when you do classical calculations, suppose let's say you are trying to find out the partition function for an interacting system.
Yes, sir.
Then also we will take only 1 by h power 3, and we don't. So it doesn't.
Yes, sir. Yeah. Yes, sir. Yeah.
Yeah. So that's not because of interaction.
Yes,
So
sir.
there's some that is this prescription of writing 1 by h power 3n is independent of your system. It's a prescription of the method itself.
Yes, yes. That means we took that these many states are available for any system.
Correct.
So, okay, sir. Yeah. Thank you, sir. Thank you very much.
Okay. So I think if there are no questions, then we can close, and we will meet on Wednesday again.